All right, lesson 2.4.1, tangent lines. This is a fairly big lesson, an important one. I tend to start it out with reminding students of the formula for average rate of change because they're actually going to be related. You might want to pause the video now and see if you can remember that from memory on your own. But average rate of change is f of b minus f of a all over b minus a. It is the exact same as your slope formula, right? The change of y's, so y2 minus y1 over x2 minus x1. The reason for that, again, is if I had some graph, let's say this was time, this was distance. The average rate of change in this case would be speed, like maybe this is in miles and this is in hours. And if I started here and ended up there, the average speed would be the same as the slope of the line connecting those 2 points, rise over run, right? So average rate of change is just your slope formula, which you should have memorized. You might occasionally see it written like this. That just means change in y over change of x. That's the exact same thing as when I wrote y2 minus y1 over x2 minus x1. Same thing. So just, you should know average rate of change. All right. There is a quick example of finding average rate of change from x equals 2 to x equals 5. If you want to see this, I'll work through it quick. Otherwise, you can skip ahead to when we get to some new stuff. But for this one, I would be doing f of 5 minus f of 2 all over 5 minus 2. Plug a 5 into x squared, that's 25, minus plugging a 2 in, 2 squared is 4. All over 5 minus 2 is 3, that's 21 over 3, which is 7. Again, if you wanted to see it graphically, here's x squared. If I put a 2 in, I end up at a 4. If I put a 5 in, I end up at a 25. And that average rate of change is the exact same thing as the slope between those 2 points. Slope equals 7, which is your average rate of change. Between x equals 2 and x equals 5. All right, or maybe instead between from x equals 2 to x equals 5. Same thing. All right, so there's the graphical interpretation. So please note, finding the average rate of change is the same thing as finding the slope of a secant line. That word secant line might be new to you, or maybe you've forgotten. Secant line is just a line that connects 2 points and goes through a function. So here's a point, here's a point. The line connecting those 2 points, that has a slope of 7. That's called the secant line. This is called the secant line. All right. The main goal for today is being able to find the slope of a tangent line, like this line right here. You'll notice a tangent line is a little different than a secant line. Yes, it crosses through, maybe, it doesn't have to. But the big point with a tangent line is it just touches a graph in one particular point, this point right here about. And in this case, I want to find the slope of the graph through that one particular point, not the average slope, like not the slope between 2 points, right? But between one. So I can find the slope of the tangent line by instead looking at consecutive closer secant lines. Like if this is a point I want to find the slope of, right through that point. So it has the same slope as the graph right there. You can see it's got the same slope. But I could take this point and that point and find the secant line. And if I look at that, I'm like, well, that's a positive slope, but not as positive as this green one. So it's close, but not close enough. If I pick a closer point, hey, that's a closer slope. That secant line, that's got a closer slope to the green line. If I pick even a closer point, that secant line has even a closer slope to that tangent line. And if I take this point and bring it closer and closer and closer to being at that point, the slopes of these consecutive secant lines will get closer and closer and closer to being the slope of that tangent line. This is that idea of limits that we've been talking about over and over again. So we're actually going to use a limit function to find that. So I can find the slope of this secant line using just my slope formula. And I'm going to start at x equals a, and then I'm going to pick a point a little bit further than a plus some h. So if a was 2, this might be 2 plus 1, which would be 3, or 2 plus 1/2, which would be 2.5. So I'm just going to find the general formula for the slope of that line. So I know how to find the slope of a secant. It's equal to f of b minus f of a all over b minus a. But in this case, my b is right here, a plus h, so it's f of a plus h minus, there's my a, f of a, all over a plus h minus a, right? And then this part here can simplify, so that would be f of a plus h minus f of a all over, the a's cancel out, all over h. So that thing is going to be the slope of my secant line. Slope equals f of a plus h minus f of a all over h. Now the thing is, again, I don't really want the slope of the secant line. Normally the more important thing is the slope of the tangent line. But we had mentioned that this secant line, the slope of that secant line is going to get closer and closer and closer to the slope of the tangent line as that second point right here gets closer and closer to being the first point. It's closer and closer to that point there. So I want this b, I want it to move closer and closer to a. Well, you'll notice, here's my a, this was my b. The only difference there is that h. It's a plus a little bit more. So I want that h to get closer and closer and closer to 0. The closer h goes to 0, the closer these 2 points go to being the same point, and the closer my slope formula gets to becoming the slope of the tangent. So the big thing for today, if this is a slope of a secant line, the slope of a tangent line is that exact same formula, f of a plus h minus f of a all over h, with the one added caveat that I want that h to get closer and closer and closer to 0, right? I want this point to get closer and closer and closer to this point, so that I've got my secant line getting closer and closer and closer to being that original point. All right, so the mathematical notation for that is a limit formula. So the limit as h approaches 0. That is a slope of my tangent line. This function is going to be a huge thing to know. We're going to give it a special name later on in chapter 3. We're going to call it the derivative formula. It's huge. You're definitely going to want that memorized. So take a moment, write it down. The slope of a tangent line, also known as instantaneous rate of change, by the way, we'll talk about that in a minute. The slope of a tangent line is equal to the limit as h approaches 0 of f of a plus h over f minus f of a all over h. That's going to be a really important formula. All right, quick practice, just to make sure we have it down. We're going to find the slope of a tangent line at 2, 4, the tangent of x squared at 2, 4. And then we're going to write an equation of that tangent line. So just to give everybody an idea of what we're doing, here we've got the graph y equals x squared. So if we want a graphical interpretation, here's y equals x squared. At the point 2, 4, so 2, 4, we're trying to find the equation of this line that goes right through that point and has the same slope of the function at that point, right? So I gotta have that same tilt, right? Like as I'm traveling along this function, right? It's got this type of slope right at that point on the curve. So I'm going to use my formula. My formula again for slope of a tangent line is a limit function. So the limit as h goes towards 0 of f of, I'll just write the whole formula out, a plus h minus f of a all over h. But in this particular case, I've got my a, right? That the point I want to find the slope at is 2. So let's be a little bit more specific. For this slope, it's going to be the limit as h goes towards 0 of f of 2 plus h minus f of 2 all over h. That f of 2 plus h just means take the 2 plus h and plug it into your function up here, the x squared function, right? Because that equation of this line was y equals x squared. So I'm going to plug that 2 plus h into there. And so this is going to simplify to be the limit as h approaches 0 of 2 plus h quantity squared minus plugging a 2 in there. 2 squared is 4. I'll go ahead and write 2 squared just because I can, all over h. I want to find this limit. I can't just plug 0 in now because then I'd be dividing by 0, which is a problem. So I'm going to hope some nice things happen. And with this formula, they almost always do. Let's square out the top. That'll be limit as h goes towards 0 of 4 plus 4h plus h squared minus that 2 squared is 4 all over h. That's going to simplify nicely because those 4's are going to cancel out, right? And then I could divide each of these terms on top by h, right? I could factor an h out and cancel that h. I don't know how you'd like to do that. I suppose I'm just going to go like this. That h, I'll be really particular, make sure we understand it, I suppose. Limit as h goes towards 0. This top, I can factor an h out. So h 4 plus h all over h. Then I can see those h's cancel out. And so I really end up with the limit as h approaches 0 of 4 plus h. And now I can plug a 0 in because there's not that problem here anymore. Plugging that 0 in, 4 plus 0 is 4. This line has a slope. All right, so that was the first part. The second part actually asked me to find the equation of the line. Then write the equation for the line that is tangent to x squared at 2 equals 4. This part should be easy, but once we get to calculus, some people forget. To find the equation of a line, you only ever need 2 things, right? Equation of a line just requires a point and the slope. For this particular line, I know the slope, that's 4. We just found that out using what's going to become calculus. So the slope is 4. And the point is right here, right? That's the point that's going through. It's going through the point 2, 4. So then I just use my equation, right? I know the point slope form of a line is y minus y sub 1 equals the slope times x minus x sub 1, right? That's the equation for a line. So just plug in your points. In this case, y minus the y coordinate of 4 equals slope, which is 4, times x minus the x coordinate of 2. You could solve for y and get y by itself if you want, but why bother? That is a perfectly legitimate form of a line. That is the equation of my tangent line. All right, that's the stuff you're going to be asked to do today. You use this little slope formula to find the slope of your line. You use a point slope form of a line to find the equation of that tangent line. What if I ask this one? Where is a slope of y equals 1 over x equal to negative 1/4? All right, so let's explore this graphically before we actually answer it. You guys should know 1 over x looks like this. If we glance at that, we should be able to see that that thing is going to have a slope of negative 1/4, not just one time, but twice. I can see that because a slope of negative 1/4, that'll be a slightly downward slope, right? Like that. It's negative, so it's going downward, down 1 over 4, down 1 over 4. I can see that right about here-ish, I'm going to have a slope that's downward, right? Then again, I'm also going to have a slope downward that's maybe right about there-ish. To find where those points are, though, let's actually use my slope formula. We know that the slope of a tangent is equal to the limit as h goes towards 0 of f of a plus h minus f of a all over h. In this particular case, I want the slope to be negative 1/4. So negative 1/4 will equal the limit as h goes towards 0. F of a plus h, plugging that into my function would be 1 over a plus h minus plugging the a in 1 over a all over h. And then I just try to calculate this limit so that I can figure out when those two are going to be equal to each other. Again, I can't just plug a 0 in because then I'm dividing by 0. So I'm going to do a little bit of math, hope something nice happens. And again, with this function, it almost always does. For this one, I'm going to find a common denominator first, right? So I'm going to multiply this by a, that by a. I'm going to multiply this one by a plus h, and that one by a plus h, because then I'll have the same denominator. This one is going to be a over a times a plus h, minus that one is going to be a plus h over a times a plus h, all over h. Combining those two together into a single fraction, now that they have the same common denominator, that'd be a minus a plus h. Well, subtracting that, a minus a is gone, so it's going to be nothing. Nothing minus h as a negative h, so I end up with negative h over a times a plus h, all over h. Taking a fraction divided by a fraction, right? I could write this as h over 1. A fraction divided by a fraction, you can flip and multiply. So that's negative h over a times a plus h, times, flip the bottom one, flip the denominator, 1 over h, right? Because multiplying by the reciprocals is the same as dividing a fraction. We will be able to hopefully see that these h's are going to cancel out. I get negative 1/4 equals a limit as h approaches 0 of just negative 1 over a times a plus h. And now I can actually plug that 0 in. I couldn't before because I can't divide by 0, but now that I wouldn't be dividing by 0, plug that 0 in. I'll have negative 1/4 equals negative 1 over a squared, because this would be a times a plus 0, which is a times a, which is a squared. We almost have this. Do a little bit of cross multiplying. That'd be negative a squared, or cross products, whatever you want to call it, equals negative 4. Multiply both sides by negative 1, a squared equals 4. Take the root of both sides, and a would be not just 2, but a plus or minus 2. So it turns out that my equation, my line, y equals 1 over x, is going to have a slope of negative 4 and negative 1/4 in 2 places. One when x is equal to 2, and one when x is equal to negative 2. Don't let this math scare you. It looks so long. It looks like a lot of work, but it's not too bad. Just take it a step at a time. If you run into problems, come see me or your teacher during office hours. We can definitely help you out with this. This is a long section. We are almost done. There's something called a normal line. A normal line to a curve at a point is a line perpendicular to the tangent at that point. In other words, it's the exact same thing as a tangent line, except it's got a perpendicular slope. It's off by 90 degrees. So I'll give you a graphical interpretation. If I were to have a tangent line would have that exact same slope of the function. Looks like about like that. That would be my tangent line. Has the same slope. A normal line is just going to go through the exact same point, but it's going to be perpendicular to the tangent. That's what a normal line is. Same as a tangent, just perpendicular slope. So we'll do one example of that, one real life example, and then we'll be done. It's going to be a little bit longer of a video this time. If you want to take a break here, now would be a good time just to hit pause, go take a little walk, kind of absorb everything you've learned, maybe do the first problems in the homework and come back. I would recommend it. Here we go, an example of finding the normal line. So I want to find the equation for the normal to the curve of 4 minus x squared at x equals 1. So we're just going to go through everything we did before. Same thing we can do is we can find the slope of a tangent. And that equation again is a limit function. So limit as h approaches 0 of f of a plus h minus f of a all over h. I recommend starting with that every time just because it's really good to make yourself memorize it. In this case, it's a limit as h goes towards 0. I want to find the tangent at x equals 1. So I'm going to do f of 1 plus h minus f of 1 all over h. I can't plug that 0 in yet because then I'd be dividing by 0. So let's start plugging things in. This would be the limit as h goes towards 0. 1 plus h, when I plug that in my function, I'm going to have 4 minus 1 plus h quantity squared minus, when I plug 1 into there, I'm going to have 4 minus 1 squared, which is 3. I'm just going to write 3. I can do that in my head. All over h. Let's square this thing out here. This will be the limit as h approaches 0 of 4 minus, all right, squaring that out would be 1 plus 2h plus h squared minus 3 all over h. All right, that'll be the limit as h goes towards 0 of 4. Let's distribute that negative, right? 4 minus 1 minus 2h minus h squared minus 3 all over h. You'll notice up here I've got 4 minus 1, which is 3, and I've got a minus 3 here. 3 minus 3 is 0, so those go away. And I've got the limit as h approaches 0. I can factor an h out of those, so I'm going to go and do that. H times negative 2 minus h all over h, which is super convenient because guess what's going to happen? Those h's are going to cancel out. Huh, that seems to happen a lot. We end up with a limit as h goes towards 0 of just negative 2 minus h. But now that I'm not dividing by 0, when I plug in that 0 for the h anymore, you can plug in a 0. Negative 2 minus 0 is negative 2. That's the slope of my tangent line. It's a lot of work. But now that I did that work, the rest of it is actually pretty easy. A question was asking me to find the equation to the normal line. Well, the equation to the normal line is going to be the exact same as the tangent line, except it's going to have an opposite reciprocal slope because perpendicular lines have opposite reciprocal slopes. Opposite means opposite sign, reciprocal means flipped fraction. So let's see if I can fit it in here. So anytime I want the equation of a line, I need two things, a point and a slope. The point, let's look back at where was I talking about? I was trying to find it at x equals 1. So it's going to be 1 comma something. So my point is going to be 1 comma something. To find the something, I just got to find that y value, right? Well, I've got this equation here, right? It's 4 minus x squared. If you wanted to see a graph of that, that'd be 1, 2, 3, 4. It's going to look something like this, right? When I plug a 1 in, I land right about here. I can find out by just plugging it into my 4 minus x squared. Plug a 1 in there, 4 minus 1 squared, oh, that's 3. So the point is going to be 1 comma 3. Over here, that was the slope of my tangent, so the slope of my normal, let's write normal up here for the normal equation. The slope of my normal line is going to be just the opposite reciprocal of that. So opposite instead of negative, it's going to be positive. Reciprocal means it flips. So instead of 2 over 1, it's 1 over 2. And so there I go. I've got a point. I've got a slope. So we just plug that into my equation. Y minus the y coordinate of 3 equals a slope 1/2 times the x coordinate, x minus the x coordinate 1. There's the equation of my normal line. If we're not sure, we can double check. It's got the point 1 comma 3 over here on my sketch. 1 comma 3, that looks like the right point. Slope of the tangent line is negative 2. If I do a sketch of that, negative 2 is down, that looks about right? That looks like a slope of negative 2. And then the slope of the normal line would be through that same point, but perpendicular. It's positive. Yeah, that looks probably like 1 over 2, 1 over 2, 1 over 2. Probably a pretty good sketch. I think we must have found. All right. Very last thing. You might recall that this equation, right, the f of b minus f of a all over b minus, do an average rate of change. Well, if I add that points in time are getting closer and closer to the same points. Like if you wanted to find average speed between, you know, the time you start at 0 and 1 hour later, you're going to take the distance you traveled, subtract them on top, minus, and divide by the hour. In this case, all right, the equation for the distance in feet that a rock travels in free fall on Earth is d equals 16 t squared, where t, when you drop a rock, the distance to travel is going to look, the distance equation is going to look like that. Y equals 16t squared. Which should make sense because as the rock is falling, it starts falling kind of slowly at first. But then as time increases, it travels faster and it just falls faster and faster and faster at a steeper and steeper slope, at a steeper and steeper rate, right? So if I wanted to find how fast that rock is traveling, I could look at an average rate of change by picking 2 points on the graph and finding this. Or I could use instantaneous rate of change and I could find the exact speed at what I'm going to do. I want to actually find the instantaneous rate of change at t equals 1 second. So let's see here, go back a little bit. If I wanted to know how far it traveled in that 1 second, I would just plug it in there. At 1 second, it traveled 1 times 16 feet in 1 second. 16 feet per second, that's actually its average speed between these 2 points. You remember it started falling slower than 16 feet per second because we've got this curve here. So we want to know how fast is it traveling, and it's probably going to be traveling faster than 16 feet per second. We just use that limit function. It would be the same as the slope of that tangent line as h approaches 0 of f of, I'll write the whole function out again, a plus h minus f of a as h approaches 0 of f of 1 plus h, because I want to find the speed at time t equals 1, minus f of 1 of, let's see, 1 plus h. Oops. That'll be plugging the 1 plus h into the equation. Instead of 16t squared, it'd be 16 squared minus, plugging a 1, 16 times 1 squared is 16. And we just keep going. Square that out. This would be 16 times 1 plus 2h plus h squared. All over h. 16h squared minus 16. I can see, look at that, those 16